Good morning to all of you. Good morning to all of you. I hope you are able to hear me. Okay. Today, once more, you know what I am going to do now. First, I am going to do a small demo. It may be difficult to do the demo on stage here, so I have got a video which I am going to play. You will observe what you observe in the video, and then we will start asking questions and we will find answers for those questions. Are you ready? Okay? Yes. Okay. Okay, what you see is actually a bed of nails. You can see the nails are very sharp and they are of the same level and they are on the wrong side up. Now normally I invite somebody from the audience to come down and lie down on it. You can see what happens to the banana when it drops from a height. It is completely pierced. So they are very, very sharp nails. Now, because nobody will come, there is no other go but for me to lie down on that. You can see I am lying down on the bed of nails. It is not just that. There will be something else. My friend waiting for me will put a plank on my chest and he will put a concrete block, normally a granite. Today it's only a concrete block. And then he will hit it with a big sledgehammer and break it. Now you can see there was a big blow. The brick is broken. Then I get up and you see what has happened. Any blood coming out at the back of my body? No. So it looks something like a magic show, except that I am not in a magician dress. And we have, there are two reasons why nothing happened. Two reasons why I do this. I do several times. Okay? I would have done one point is simple physics will save you. There is only some simple physics. There is no godliness or any saintliness associated. Number two, I want to prove that life in IIT is not bed of roses. Some of you might think. Okay. Now my weight is nearly 70 grams, 68 grams to be precise. Let us take it as 70 grams. When I lie down, there will be about 1000 nails below my body. There are about 2000 nails in the board. At least 1000 will be below my body. Nothing happened to me. 70 kilogram weight on 1000 nails. Nothing happened to me at all. Why? I'm sure some of you would like to answer, but to make the story short, you know, the total weight is distributed on 1000 nails. Therefore, the weight is shared by different nails. If you look at the weight on each nail, it will be around 70 grams, 0.07 kilogram or about 70 grams if I take 70 kilogram and 1000 nails. So, you find because the weight is distributed, nothing happened to me. But then, you put a plank, you put a concrete block and you hit it with a sledgehammer. Sledgehammer is a big hammer. Okay, you hit it and you can see the blow was very strong. Okay, usually it will be done by my student, and when there is an opportunity, how the students will make use of that. Okay, he will hit it with all his might, and then still you found the brick broke, but nothing happened to me. Why? If I hit a nail with a large force like the hammer, it will even pierce into your concrete wall, but nothing happened to me. Why? Again, I'm unable to interact with you. It will be very interesting to get answers, because normally I like wrong answers. I don't like right answers, because wrong answers, there is nothing like right and wrong in science. We all know that. Somebody says something, somebody else will come and say it is not quite. Newton said it is all gravity. Then Einstein came and said something. Then people said, well, Newton is right, but not quite. When velocities are very close to velocity of light, Newton can be wrong. That's what they found. So in science, it doesn't matter whether a particular answer is right or wrong, but then we have to analyze, understand, and if it explains correctly the principles, using the principles of physics, the observation, we accept it as part of science. Otherwise, we discard and go to the better answer. That is the normal way science progresses as we go along. So here, this large hit of the hammer is not a force. First you should recognize it. It is an impulse. Some of you murmuring, I can hear. It is an impulse. What is an impulse? The large force acting for a short time. So because it is an impulse which happens only for a very short time, you find there is some wonderful principle that comes out of Newton's first law, namely inertia. You know what is inertia? Means laziness. Every body continues to be in a state of rest on Sunday morning unless compelled by external force, right? Something very similar to that. So because of the inertia, the entire energy is received only by the brick. There is no time for it to convey it to the plank or to the body, and therefore it makes the brick break. There is dissipation of the energy there, and nothing happens to the person below, and therefore we are safe. I am still safe and talking to you now. Okay, so this is a very simple experiment, but it can be tried in other ways. You can put pin and blow a balloon and put it there and put a book, and the balloon will not pierce. Okay, if I take one single pin and put a pin inside the balloon will burst. So you can try some of the simple experiments. Don't try this nail bed without somebody's support and supervision. Okay, some teacher supervision. Okay, so that is about warming up. So getting into the physics mood, no? The players, when they go for games and all that, they have to do the warm-up exercise. So every day I want to try a simple warm-up exercise so that you get into the physics mood. Then if I say all sorts of things, you will be able to follow me. That's the only idea. Now let us proceed with our discussion that we had yesterday. Okay, we talked about in detail plane polar coordinates. Right? Then we also obtained, using plane polar coordinates, the expression for velocity, especially when it is function of time. We got, you may remember, some of you may even remember, so this is the velocity along the radial direction, rho dot. Rho phi dot is like r omega. Rho is like something like r, phi dot is like omega d phi by dt. So this rho omega gives me the angular velocity. This is the radial velocity, this is the angular velocity in the case of a plane polar coordinate. Similarly, we note the expression for the acceleration by differentiating this, remembering E rho E phi also will change with reference to time. That we have already seen. I want to go back into that. So you will find rho double dot minus rho phi dot square along E rho plus 2 rho dot phi dot plus rho phi double dot along E phi direction. Okay. So this is the expression for the acceleration in plane polar coordinate. So we got these two expressions. These are all useful for solving simple problems involving all these things. I gave you some simple examples also of a uniform circular motion, accelerated circular motion, etc. Now this is only for 2 dimensions. This is only 2 dimensions. So we have to go further to 3 dimensions. That is a dimension that we are all familiar with. You have x, y and z. 3 coordinates are there. Here we have equivalent xy, rho and phi. So we have to have another z. Well, because z is already there in the vertical direction, we will take rho phi on the horizontal plane, xy plane, and z we continue to bring it into our thing, and then that coordinate system is called cylindrical coordinate. So in a cylindrical coordinate system, in a 2 dimension it is rho phi, in a cylindrical thing it is rho phi and z. So if I have these 3 numbers, rho, distance from a chosen origin, distance from a chosen origin, if I say this as my rho, now I can drop the perpendicular from here, and you see I can have a this will be my rho, this will be my phi, because in the xy plane we have the plane polar coordinate rho and phi, and if I take a point which is rho, phi and z, so I have rho and phi, and then go rho meters with an angle from x-axis phi, and then go along the z, you will reach this point, just as you have x, y, z in the rectangular Cartesian system. So you have rho, phi and z, that is what the coordinates of the P are. Now if I do that, the first thing that we will do is we will try to find out what is the equivalence. How do I convert from cylindrical polar to the rectangular polar? Before that, we can see, we have already seen the limits of rho and phi while discussing plane polar coordinate. 0, this will be the range of rho. Rho can be from 0 to infinity, from the origin to infinity, anywhere in the plane. And phi, this also you know, 0, phi can be anywhere. This is azimuthal angle we say in the plane of xy. So it can go throughout 360 degrees, which is equivalent to 2 pi radians. So phi will be between 0 and 2 pi radians, rho will be 0 to infinity. And what about z? Z is, you can go as well as the below the plane, top and bottom. So minus infinity and plus infinity. So z takes care of the third direction, rho and phi takes care of the horizontal plane like the xy plane. So these are the limits of the various parameters that we use, rho, phi, z. Now we can try to find out what are the equivalent x, y, z, right? Now you can see what is x. So the same point can also be reached by coming this distance along x, this distance along y parallel to y, and this distance along Z. So this could be my Z from here to here. This will be my X, and this or this will be my Y along the Y direction. So what is this? This is rho, this is phi. So what is this? This is rho cos phi, and this will be similarly rho sin phi. Okay, therefore this we know already. This is the same thing we looked at in the plane polar coordinates. Okay, so I can write here x will be rho cos theta, y will be rho sin theta, and now z will be z. Z is same in both systems. Rectangular system, z is normally we take it as vertical axis, and here also because rho phi cover only the horizontal plane, the vertical plane can continue to be z. Therefore this is much simpler than what it looks. And we also know what is rho. Rho is in terms of x and y. Rho is x square plus y square. You know that. These things we have seen it. And tan phi is equal to y by x. We have seen all these things earlier. There is nothing new. I am not giving anything new here. Now we have to define some unit vectors. We have done some unit vectors already in the plane polar coordinates. What are those things? You will take some unit vector along the rho direction, which we call E rho, and some along the phi direction, phi increasing direction, which we call E phi, and some along the Z direction, which is Ez. Even though I draw here because I want to show the direction, I can draw it from one point. If I take like this, I can say E rho is something like this in the xy plane, and Ez is something like that, and you find E phi is somewhere here. So these are again we have already found E rho and E phi are perpendicular to each other all the time, and Ez is perpendicular to the plane, and therefore that is also. So you have three mutually perpendicular unit vectors. That is what we have. Three mutually perpendicular unit vectors. They are now E rho, E phi, and Ez. Now we can write E rho, E phi, and Ez in terms of Ex, Ey, Ez. Just as we are relating here, we can also write in terms of the other unit vectors. So E rho will be on this side cos theta, cos phi along Ex direction, and similarly along the plus sin phi Ey, and similarly E phi will be minus sin phi Ex plus cos phi Ey, and Ez will be same as Ez. Okay, both are same because they are in the same direction. So these are the relationship between E rho, E phi. How do you get it? Exactly like this. Rho is now 1. So Ex will be E rho cos, along the x direction. So this will be 1 cos theta Ex along the s direction, 1 sin theta Ey. That's what I have written. When it comes to E phi, you will find it is minus sin phi. I explained when I discussed plane polar coordinates, therefore I am not going into this. Similarly, I can write the other one in terms of Ex, Ey, Ez in terms of E rho, E phi, Ez. I can write this. You know that. This looks like a matrix which we have already seen, transformation matrix between E rho, E phi, Ez and Ex, Ey, Ez. There is no Ez, 0 times Ez, 0 times Ez, 1 time Ez, 0 times Ex, Ey for the Ez, and that's why you will get a matrix which we have written number of times. If you want, I'll write once more just to make it clear to you. So the same equation I can write it as E rho, E phi, Ez is nothing but cos theta, sin theta 0 minus sin theta, cos theta 0, 0, 0, 1 multiplied by Ex, Ey, Ez, unit vectors. So this is the transformation matrix. Using E rho, E phi, Ez, you can express it in terms of Ex, Ey, Ez by performing matrix multiplication. You will get the same equation as you have got here. Actually, I will say 0 times Ex plus 0 times Ey plus 1 time Ez. Similarly, 0 time Ez for the rest of the things, 0 time Ez. So, cos phi, sin phi 0, cos phi, sin phi 0, minus sin phi, cos phi 0, minus sin phi, cos, I should have put cos 5, all of them should be 5, I am sorry. Then 0, 0, 1, 0, 0, 1. So that is what we have as a transformation matrix. Now in such things, you know, if I bring this Ex, Ey and take it on this side, what will happen to this matrix? The matrix will become the transpose of this matrix. So if I want to if I say in terms of Ex, Ey and Ez, then I can represent in terms of rho, phi and Z by simply leaving the diagonal, changing all of them. So this sin phi will come here, so it will become plus sin phi. This minus sin phi will go there, so it will minus phi. This 0 will come here. That's all. So you find this is a reverse transformation from XYZ. If I want to represent in terms of E rho, E phi, Ez, this is the way I do it. Okay. So I can write those equations here. That's what I wanted to write, but now I have explained with a matrix, so I'm not going into that. Because I said even here, just as in the rectangular coordinate system, Ex, Ey, Ez are in 3 mutually perpendicular directions. Even here at this point there will be 3 mutually perpendicular directions, E rho, E phi and Ez. This is Ez, this is E rho increasing and this will be phi increasing. So that is what it is. So this also is mutually, but one difference, what is that? If the radius vector changes position depending upon the motion of the body which you are following, you would find the E rho, Ez, E phi will also keep rotating along with that. So unlike in rectangular coordinate system, Ex, Ey, Ez not changing at all throughout. Ex is always Ex in the same direction, Ey in the same direction, whereas here this keeps on changing. As I change the position of the point P anywhere, you find the 3 mutually perpendicular unit vectors E rho, E phi and Ez are not pointing in the same direction, they also change. This is something which I keep on telling you, and so you should remember that. So these are all not constants in terms of direction, they keep changing. And because they are mutually perpendicular, I can immediately write something which you all know very well. E rho dot E rho. They are mutually perpendicular. So what will happen? E phi dot E phi. What is the angle between E phi and E phi? 0. What is the angle between E rho and E rho? 0. What is the dot product? Magnitude of E rho, magnitude of E rho, cos of angle between them. Because if they are both are same direction, the angle is 0. Therefore, cos 0 is 1. Should be equal to 1 because they are in the same direction. And if I put E rho dot E phi, you know, it is also E phi dot E z is equal to E z dot E rho in a sequence, and that is equal to 0 because the cos of the angle between them is 90 degrees. E rho and E phi are perpendicular to each other. E phi in E z perpendicular to each other exactly. So you find this is something which you know. I can also add one more thing. E rho cross E phi, if it is a cross product, what will happen? 90 degrees, you know. Therefore, sin 90 is 1. E rho E phi should be 1. But then this cross product will always result in a vector which is perpendicular to the plane containing A and B, if it is A cross B. Therefore, I should have the third perpendicular direction for this, and that is Ez. Similarly, E phi cross Ez is equal to E rho, and Ez cross E rho is equal to E phi. So this also we should remember. All these things will be useful when you start solving problems. Okay. The other things also we should remember, and that is what is d rho with reference to d phi. D rho by d phi, when you actually perform the differentiation with reference to phi in this equation, E rho, I'll take that just for once. E rho is equal to cos phi Ex plus sin phi Ey. So d E rho by d phi will be d E rho by d phi. You will find this will be along the, it will become minus cos phi sin phi. This will become cos phi, and that is nothing but the other one. So this is, if I say E phi minus sin phi Ex plus cos phi Ey. So if I perform the differentiation of E rho with reference to phi, cos phi will become minus sin phi will become cos phi. That means they resemble this, therefore it is E phi. Similarly, d E phi by d phi is also equal to minus E rho. You will find this also will be minus, this will also become minus, but this will become cos, this will become sin. So there are two minus. If I take the minus, it will become this, that is E rho. The minus sign is outside, therefore it becomes minus E rho. So these things you should remember, as well as if I represent a general vector A, how do I represent? I have to represent in terms of Ax, Ex plus Ay, Ey plus Az, Ez. In a similar way, we have to say A rho, where A rho is a component of vector A along the rho direction, E rho plus A phi, E phi plus Az, Ez. That is how we write. Okay, in a general thing. Once we do all the things, we can write the position vector or in this cylindrical polar coordinates. What will be the position vector? We already know this is what it was in plane polar coordinates. So if it is a three-dimensional, I have to also have something along the Z. Therefore, I should include yes, Z, Ez. So this will be the new position vector. If you want, I can put it like this: new position vector in cylindrical polar coordinate. Now you may be wondering why we call it as cylindrical polar. Why do we call it cylindrical polar? To understand that, we will try to find out what kind of surfaces they will generate for the following condition. For if I say, for example, rho is equal to constant. If I say rho is equal to constant, what kind of thing you will get? Geometry in this cylindrical polar coordinate system. If I have rho is equal to, what do you mean by rho is equal to constant? The distance on the xy plane, rho phi plane, distance from the origin to the point is always the same. So if I cover all the points which are there, you would find I can cover a circle in the plane. But then I have to cover in 3 dimensions. The phi also can go from 0 to 2 pi. Z can go from plus infinity to minus infinity. Therefore, if I do that, the circle will start moving in the vertical direction. So what I will get will be a cylinder going to plus infinity and minus infinity. Okay, this is what I will get. This is rho is equal to constant surface. So rho is equal to constant means phi and z can take all possible values. Phi can go from 0 to 2 pi, z can go from plus infinity to minus infinity. So if I keep r only, rho only constant, I will get a complete cylinder for this surface. Similarly, if I say phi is equal to constant, if phi is equal to constant, you know this is the phi. So you can see I can draw a line like this. So this will become this phi is a constant always. So I can go along rho anywhere from 0 to infinity, from here to infinity, from here to infinity. Phi is constant. And I can go in the 0 also. That means this plane can go up. So it becomes a single plane like a open page in a book, which will be going from plus infinity to minus infinity on the z direction, from 0 to infinity on the r direction, because phi is a constant. So it is a plane. So rho is equal to constant gives me a cylinder. This gives me a plane. Now it is very simple, plane passing through the origin and having a constant angle phi with the x-axis. Then one more we have, z is equal to constant. Z is equal to constant means what? It is always at a distance z from the plane. So it will be a plane which is horizontal parallel to xy plane, and that will be what we will see. It becomes complicated to draw in this, but you can imagine. So if I say z is equal to, this is a constant, say for example 5 units or something, then I can imagine a plane cutting the z axis at z is equal to 5 and then going in all directions. So that will be the z is equal to constant plane. So it is important to remember what will be the type of surfaces we generate for the various things. Rho is equal to constant will be a cylinder going up to infinity parallel to the z axis. Z axis will be the axis of the cylinder. Phi is equal to constant will be a plane which is again parallel to z axis, passing through the z axis, containing the z axis and going to plus infinity, minus infinity, etc. Z is equal to constant will be a plane parallel to the xy plane or rho phi plane, and that also is seen. Now I can slightly complicate a little more and say what will happen if rho is equal to constant and phi is equal to constant. What will I get? So rho is equal to constant will give me a cylinder. Phi is equal to constant will give me a plane. So the plane will be cutting the cylinder at some angle phi. So what will I generate? I will generate two parallel lines which are the sides of the cylinder going up to plus infinity to minus infinity. That's what I will get. Similarly, I can get what will happen if it is rho is equal to constant and z is equal to constant. So rho is equal to constant is a cylinder, Z is equal to constant is a horizontal plane. So I cut a cylinder with a horizontal plane, I will get a circle. So when I have two surfaces meeting, I will get a line or curve. In this case, I get a circle. In this case, I get the line. Okay, I hope you can see that. So we can keep on looking at all the other similar effects. Okay. It is also important to define some more things. Let me draw. So I can imagine a very small volume. The sides of the volume are, if I have here rho, on the other side I have two lines, rho and rho plus delta rho. Similarly, I can have phi angle and small angle phi plus delta phi. Similarly, Z and Z plus delta Z. Then I can try to find the small volume that is formed by the extensions delta rho, delta phi, delta Z. You find, because this is rho, this is delta phi, this will be rho into delta phi, this distance. So one side here, this will be rho into this is R, and this will be rho delta delta rho. Okay, and then you have Z, this will be delta Z. So if these are the three sides of this small box. If in the limit they all tend to 0, I can write them, the volume element, as, say for example, dV volume element is d rho, then rho d phi and dz. So this is one side of that rectangular box. Rho del d phi is another. This d phi is an angle. So radius into that angle, small angle, gives me the arc. That arc in the limit will be straight line. So we can assume this to be the one of the side, and dz. So you should not read it as d rho d phi dz. You should remember this is d phi, d rho, dz. So d rho d phi dz. So we normally write it as rho d phi dz. This is the way we normally. This is the volume element. This will be useful. Now if I have a volume element, I can find out what is the volume of the cylinder. If I do it using x, y, z for finding the volume of a cylinder, it will be very, very complicated mathematics. Whereas here it is very simple. If I want V, volume of the cylinder, I have to integrate dV. I have to integrate, but dV has three variables, d rho, d phi, dz. Therefore, I will have to put three integrals, rho, d phi, dz, and rho goes from 0 to some r if the cylinder has got a radius r, and phi goes from 0 to 2 pi, we have already seen, and z can go from 0 to h, where h is the height of the cylinder. So I have a cylinder of height h, radius r, and I want to find the volume. So I just integrate. This is a triple integration. Now, because they are independent, I can take rho d rho. If I take, it becomes rho square, that is, if I apply the limit, it will become r square by 2. Rho square by 2, rho d rho, that is r square by 2. d phi between 0 to 2 pi will give me 2 pi. dz 0 to h will become h. So if I remove this, I get pi r square, which you know is the volume of a cylinder. So you find in 2 lines I am able to find the volume of a cylinder. So that is there because you have the symmetry and you have chosen a coordinate system which matches the symmetry of the problem, and therefore the problem becomes rather straightforward without very complicated mathematics. So that is one of the reasons why we study about cylindrical polar coordinates, spherical polar coordinates, plane polar coordinates, etc. Just to show you the effect of that. Okay. Similarly, I can also have small areas. For example, this area which is in front of us. You know, this is Z, this is rho del phi. So that area will be rho d phi dz is an area which is along what direction? Area is a vector, we all know that. It comes out of rho, it is a cross, you have to do the cross multiplication, and if you do, that means the direction will be the third direction, which is in this case the, what is that, rho d rho, is it on the e rho direction, because this is along the this is along the zero direction. That means that similarly, if I want phi, I should say d rho dz will be the thing along the phi direction, and az will be rho d phi and d rho, that will be along the ez direction. So what are these things? These are elemental areas. These are elemental areas, so you should know all of these also. These are vectors, as you can see, along the e rho direction, e phi. So normally we represent an area by the normal to the surface. That is what I have done that. So now we will move on to get velocity and acceleration in the cylindrical polar coordinate system. I have already written the position vector, which is rho e rho plus ez ez. Then if I want velocity, what do you do? Velocity is equal to r dot, that will be equal to, I have to differentiate this. We have done that before. If I differentiate this alone, I will get this, like what I got in the plane polar case, I will get. So in addition, I have to differentiate this. So I have to add to this another term. So it is rho dot e rho, I am not going into the details, rho phi dot e phi plus differential of this, it is z dot ez. Here ez is always constant in the same direction. Therefore, we don't have to worry about differentiating ez. This is velocity. All that I have done it, I have added one more term here for the z prime ez. Same to do for a, which is r double dot, and that will be equal to same as this, rho double dot minus rho phi dot square along e rho plus 2 rho dot phi dot plus rho phi double dot along e phi plus ez double dot along ez. So you find it is the same as this, plus here I take the acceleration along the z direction, which is z double dot ez. So this will be the position vector, velocity and acceleration in the cylindrical polar coordinates. And as I said, they will be very useful in solving many problems. Okay, I told you. So let me quickly take one simple conversion problem. I will take simple problems, because very complicated problem I will give it to all you. You will try and solve it. So you have a location, -6 2√3, -4 are the Cartesian. That means x, y, z. Obtain equivalent rho phi z. That is, express this in terms of cylindrical coordinates. What will you do? Rho is equal to x square plus y square square root. We have already seen that. So if I put, what is x? X is 6, this is x, this is y, this is z. So 6 square is 36 plus y square is 4 into 3, 12. Okay, that will be equal to 4√3, I suppose. Okay, similarly, what is phi? Phi is equal to tan inverse y by x, that is equal to minus 2√3 by 6. That will give me pi by 3, I think. 11 by 6 pi. That will be the answer for this. You can check. And what about z? Z does not change in cylindrical polar coordinates. So it will continue to be -4. So the new in the rho phi z component in cylindrical, I will have 4√3, pi by 6, 11 by 6 pi -4 are the three coordinates representing the same point, which is represented by 6 minus 2, 3 minus 4 in Cartesian. So this presentation are equivalent. We are finding from the Cartesian this. We can also do the reverse. I leave it to you. We can do that reverse. That is, from here you have to get these things if somebody gives you. Okay. And if I want to represent the corresponding vector, what will I do? The radius vector will be 4√3 along the e rho direction minus 4 Ez. That is all. We won't use this because rho e rho plus Ez. So that is all we have here. So this will be the corresponding vector, position vector corresponding to this point. So that completes our discussion on cylindrical polar coordinates. So we may have to move to the next one, which is spherical polar coordinates. Okay, but before I go into that, I want to see whether you have any specific questions which I need to answer. So if you have got any question on the present topic or whatever that I did before, which is basically very limited, basics of vector algebra, then I did some plane polar coordinates, now today I did cylindrical polar coordinates, next I will go on to spherical polar coordinates, then we will go into more detailed discussion about how these things will be useful in physics. Okay. Is there any questions which you want to ask? Please feel free. We have a few minutes to answer. You can say it or you can send it through chat mode. I'll try to answer. If you are not able to follow, if I am doing it fast or any difficulty you have, you can always feel free to tell me. I'll be very happy to modify, because feedback is the most important part of any learning, including in electronics, feedback everywhere. Feedback means control. Yes, is there a question? So you have to keep on telling me whether you have any difficulty in following my lectures. I will, if it is there, then I will try to modify so that I make it more meaningful to you. If there are no questions, then I will now start going briefly into the next topic, which is spherical polar coordinate system. Okay. I will give an introduction today. Tomorrow, next time, we will discuss in detail, okay, like what we did in cylindrical. In a spherical polar, you have R, okay, and you have theta and you have phi. These are the three coordinates. Just as you have x, y, z or rho, phi, z. This is Cartesian, this is cylindrical polar, this is spherical polar. That is the reason I used rho instead of r, because tomorrow you should not confuse with rho and r. I cannot call this also, even though they are almost same, rho and r. So this is rho here cylindrical, r in spherical polar. That means I have two angles now. So far I have only distances, two distances and one angle. Here one distance and two angles. These are the thing. Therefore, what you can immediately say, I must represent correspondingly ER unit vector, E theta unit vector, E phi unit vector. And you will also see these vectors are also orthogonal. They are orthogonal means what? They have 90 degrees in between. ER, E theta, E phi, they again form a rectangular triad like this x, y, z. Okay, but then like in the cylindrical polar, here also as I change the position, the three axes will start changing. Okay, therefore there can be a function of position as well as function of time. When something moves, I want to observe the movement of our body or something like that. So that you should remember. And then I can try to write ER, E theta, E phi, Ex, Ey, Ez, because that is the most familiar system for us. So I can write and in the form of a matrix, and I can also get the corresponding transformation between the two things. So if I take, I will just briefly show you what I want to do. X, Y, Z. Now, if is a point P, I again drop a perpendicular on the xy plane, and this is my R vector, position vector. This will be my rho vector, which is on the xy plane, and this angle is what I call theta, and this angle is what I call phi. The angle between the position vector and the z axis is what we call phi. The angle between the x axis and the projection of the R on the xy plane, which is rho, is what we call theta. Some people call it theta phi, phi theta, doesn't matter. As long as we are consistent, we have to write everything correctly in this form. So once you know that, we can immediately see, I can drop a perpendicular from here, okay. Then I can find out what is this length. This is rho cos theta. This will be rho sin theta. But how do you get rho? Rho you get as, see, this is R and this is if I do like that, this will be R cos phi. That is what it is. Projection of R onto the Z axis. This is phi angle. Therefore, R cos phi is this distance along the Z, and this will be equal to this, and this in this right angle triangle is R sin phi. So my rho will be R sin phi. So rho cos theta, my x, this will be my x, this will be my y. So x will be R sin theta, and that is to be projected onto x. So R sin theta cos or sin phi, sorry, R sin phi cos theta along the ex direction. R sin phi cos theta is this distance, R sin theta is this distance. So y is equal to similarly, sorry, plus y, x is this much, and y is R sin phi sin theta, okay, and z is R cos phi, or cos phi. So this is the relationship, and I can now write Ex, Ey, Ez, or in this case, if I take R increasing, R is increasing this way. Therefore, I will call this as my ER unit vector, a new unit vector in spherical polar, and the theta is increasing in this direction. So I have to put something like that. That is my E theta, and phi is in. So this will become my E phi. So ER, E theta, E phi. Again I get three unit vectors which are mutually perpendicular. This is like this, and this is like this. So you find again you get mutually perpendicular, and we can write the expression for ER, E theta, E phi, making use of this already I have written, and then we will see elemental volume, how do you represent in spherical polar thing, how to get acceleration, etc. That we will push it to next. Thank you for your attention.